My name is Joyjit and I'm doing my research at the University of Hull, and my research topic is related to making intelligent decision support system for operations and maintenance of wind turbines. So I'm specifically looking at offshore wind turbines in my research area, and we are looking to develop a system which is transparent, interpretable, and above all which is scalable, and it can be adopted from one wind farm to another wind farm. So to start with, right. So firstly, I would give you a brief introduction of wind energy in its current state. So wind energy is clearly leading energy resource, which is very popular for tackling climate change. And wind turbines, they generate lots of data from various sensors which are there through the SCADA information. And these have previously been utilized for predicting faults in various subcomponents of turbines, such as the gearbox and such as the generator and so on. But the problem with the present approach in research regarding predicting faults in wind turbines is that although we are able to predict faults, but the problem is we are not able to generate transparent and interpretable decisions regarding how the engineers and technicians they can avert and prevent these faults. So that's the key thing I'm looking at in my research. And turbines, they of course they aren't like free of problems. They use a lot of raw materials, and there are other issues as well towards construction of turbine blades and so on. So I believe that this is a big research area in which a lot of things can be done. But in my topic, I'm trying to approach an intelligent decision support system for O&M of wind turbines, which is human intelligible, and we can predict faults as well as the corresponding maintenance actions. So here below you can see on the right hand side the power curve of a turbine. So that's a 7 megawatt rated turbine, offshore wind turbine in Scotland, which we used as our data set. Right. And the turbine is restricted to operate at 6.5 megawatts due to the issues of noise curtailment and requested shutdowns. So the red points you can see in this graph, they denote the anomalies or the different types of faults which occurred in the turbine historically based on the historical alarm data. And associated with each type of fault is a corresponding alarm message, which describes briefly what kind of fault occurred in the turbine, and based on that the maintenance engineers can take the appropriate actions. So this is just a tabular representation of how the SCADA features look like. We have the different timestamps for the different sensor data, and we have various features based on which the corresponding event description for the alarm is available historically. So the key goal of my research is to develop a system which is able to predict alarm messages alongside the corresponding maintenance actions. And in this regard, on the right hand side, you are able to see the word cloud of different alarm messages which had historically occurred in the turbine. So it is an interesting thing here that wind turbines, though they may appear as a complex engineering system, but still they have lots of unstructured data which is generated in huge amounts based on alarm messages and historical fault logs, work orders, and so on. So I'm trying to use these resources to develop the intelligent decision support system. On the left hand side, you can see the briefly the approach, which is to appear in the upcoming paper, but I would share you in a brief approach that what we do is we use these features from the turbine, which is the historical data we have alongside the corresponding logs of error messages and maintenance actions. And our goal is to use an encoder decoder architecture which can take in the sequence of features as inputs, and it can generate the corresponding alarm messages and the maintenance actions. And you must have heard about the sequence to sequence models, and more recently the transformers, which have seen immense success in neural machine translation. So based on this, we are trying to use these types of models in taking in the types of alarm messages, and based on the alarm type, we are trying to predict the corresponding maintenance action. So if there is a fault in the IPR fault fast frequency change, we are trying to generate the corresponding maintenance action that the engineer and technician can look at, and he can make the appropriate decision. So here are some initial results from our research in which we try to use sequence to sequence models with and without attention and a transformer. And as you can see, these are the alarm messages which were generated based on different types of faults in the turbine, which had historically occurred, and we try to see that where the things go right and where they go wrong. So as you can see, the transformer, it clearly it generates the best alarm messages in comparison to the other models, and these are more coherent, and these have higher blue scores. When we check the blue scores, these are much higher than the other two models. And the second advantage which the transformer provides is the different types of attention scores we get based on different types of faults. So we are able to achieve this using the alignment and context vector in the transformer. And here is just a small example of a fault which occurred in the gearbox historically. And we are able to identify the different types of features such as the bearing and the other features like the gearbox oil temperature went high, and what kind of things led to the fault. So
Joy, sorry to interrupt. So the time is up. Do you want to conclude your presentation?
Sure. So to conclude, I would say that our initial results show that the transformer is the best model out of the other two models in generating alarm messages. And we are currently looking at generating maintenance actions from transformers. And we are trying to use unstructured data such as maintenance manuals and briefly generate a knowledge graph out of which we can extract the corresponding actions based on the types of faults. So that's it. Thank you.